Everyone, welcome to topic 4.7, types of chemical reactions. By the end of this, you should be able to identify a reaction as acid-base, oxidation, reduction, or precipitation. There are some additional things we will cover in this, including redox or oxidation states and the assigning of oxidation numbers, as well as acids and bases and their conjugates, and a little bit of reaction types in detail. So without further ado, let's begin. There are a few basic types of reactions that we see in chemistry. These should be reviewed for the most part. Composition, which is also called synthesis or combination, decomposition, single replacement, which we are now calling single ionic replacement, double ionic replacement, combustion, which includes that of a hydrocarbon or a metal. All of these can be considered redox or oxidation reduction reactions except for the double ionic replacement. Acid-base reactions involve the transfer of one or more protons between chemical species. Okay, this is our Bronsted, Lowry definition. If you're looking in the textbook, you'll see those. Oh, there it is. According to the Bronsted-Lowry definition, acids are proton donors and bases are proton acceptors. The Arrhenius definition focused on the location of the hydrogen being on the acid and that the base had an OH component on it. However, that significantly narrowed the field of what was considered an acid and a base. Bronsted-Lowry expanded upon that to include proton donors and proton acceptors. And if you were to move on further in chemistry, we don't cover it as much in detail here, but you may also look at Lewis acids and Lewis bases. We'll touch on it, but not in as much detail as if you are going to continue in college in chemistry. So when the hydrogen ion reacts with water, hydronium ions form. The terms proton, hydrogen ions, and hydronium ions are all used interchangeably in acid-base chemistry. Not always, but in acid-base chemistry, when we say, hey, there's a proton, we usually also mean that, hey, there's a hydrogen ion. The hydrogen ions don't exist on their own. They're usually hooked up to the hydronium ion. Okay. So here in this image, we have the formation of hydrochloric acid in an aqueous solution. So when we say hydrochloric acid, we do not mean that HCl, as it is right here, is floating around in water. Strong acids completely dissociate, which means that the anion and the cation, so the proton and the anion, whatever it is, separate. Well, the proton then goes and hangs out with water and becomes hydronium, and the anion is floating around in solution. There's still charge balance, but it is separate. Okay. From here, when we have our our acid, hydrochloric acid, HCl, so that would be its acid. When it becomes just chlorine, or the chloride ion, that becomes its conjugate. And since hydrochloric acid is an acid, its conjugate is considered a base. So this would be its conjugate base. And then water is accepting the proton, so that makes it the base in this reaction. Now it is what's called amphoteric, meaning it can act as both an acid and a base. It can donate a proton as well as accept a proton. So since it can do that, it can be either one, but in this case, since hydrochloric acid is acting as the acid, it gets to act as the base, and so then the hydronium ion is the conjugate acid, which fits because the hydronium ion has an extra proton that it could donate if something that was a better base than water came along. And we'll get into that in more detail as we progress. There is an additional unit later on this school year where we will dive deeper into acid-base chemistry and look at what happens if we don't have a very strong acid reacting with a very strong base, or looking at just strong acids and strong bases. So we will come to those. So conjugate acids and bases exist, and they are important to remember when we're talking about acid-base chemistry. In this example here, water is acting as the acid, so different from prior, where it is going to give up the proton, so donate the proton to the ammonia, which is a common weak base. So it'll accept, because it's a base, it will accept that proton. Okay, so that means that this is our base, this is our acid. That means that the ammonium, the NH4 ion, is the conjugate acid, because this is our conjugate acid-base pair here. And then water and hydroxide, this is our conjugate base. Okay. If we look at our next example, we see a more detailed version of the image that was shown prior, where water is acting as a base and is accepting the proton. Okay. And as mentioned prior, substances that are able to act as acids or bases are called amphoteric. Water is a big amphoteric molecule, able to accept and donate protons. So acids and bases are described as being strong or weak. Strong and weak describes the extent that a substance will dissociate or ionize in solution, so split apart. This is based on the nature of the substance. Strong means that the substance will completely separate into its ions, whereas weak means that the substance will only partially separate into its ions. This is different from descriptors of concentrated and dilute that refer to molarity. So concentration has dilute and concentrated to refer to its molarity. This is very different than if we're talking about a strong or weak acid. Okay. And then we have several equations, and these are on your equation sheet, noting that if you have an H+, you can easily replace it with OHs in these equations. But you have to do both. You can't just do one. So if we were to do this first one here, it'd be negative log of the hydroxide ion, OH, is equal to POH. If you switch one, you got to switch the other. Okay, continuing further, oxidation reduction reactions involve the transfer of one or more electrons between chemical species, as indicated by changes in oxidation numbers of the involved species. Combustion is an important subclass of oxidation reduction reactions in which a species reacts with oxygen gas. In the case of hydrocarbons, carbon dioxide and water are produced in a complete combustion. In some chemical reactions, there is a transfer of electrons between two of the substances. When this is occurred, so when we transfer electrons, this is considered a redox reaction. Oxidation refers to the loss of electrons, while reduction refers to the gain. A way to remember that is that Leo the lion says grr. Okay, where the loss of electrons is oxidation. So loss with the L of electrons is oxidation. And the gain of electrons is equal to reduction. So L-E-O, Leo says G-E-R, grr. Okay, so it's an easy way to remember that relationship there. So looking at this reaction below, we see that it is a single ionic replacement reaction. To see that it is a redox reaction, we need to write the net ionic equation. there is a way to skip past this part. We will go over that later. So we have our overall and our net ionic. What we notice is that a couple things. First, that the total charges on both sides are equal. In addition to that, the amount, just like before, the amount of each atom is equal. Okay, so electrons are equal as well as the number of each type of atom. Okay, so notice that the copper ions were changed into copper metal atoms, while sodium metal was changed into the sodium ions. Copper had to gain 2 electrons to end up with a 0 charge. That means that since it's gaining electrons, so copper gained 2 electrons, that is reduction. So copper is being reduced, because it's going from positive 2 to 0. Okay. Each of the sodium atoms lost an electron to form the ion. So because it's losing an electron, it is oxidation. So we can assign oxidation numbers to each of the atoms in the reactants and products. This is an effective way to identify the oxidized and reduced species in a redox reaction. One way to determine the substance that is oxidized or reduced is to look at the oxidation number. Every particle has an oxidation number associated with it. The oxidation number compares the number of protons with the number of electrons assigned to that element. The oxidation number can be the charge on the atom, but sometimes it is not. Oxidation numbers are a way to track the ownership of the electron, so who's got the priority on that. An increase in oxidation number indicates that an oxidation has taken place, while reduction in the oxidation number shows that a reduction has taken place. There are some rules that you will need to learn in order to assign oxidation numbers, and they are listed here. Okay, elements are always 0. That includes diatomic elements. Hydrogens in compounds are always +1, except when it is a hydride ion. A hydride would be like the sodium hydride here, where hydrogen is a -1. Oxygen in a compound is always -2. Peroxide is -1. The other exception I'm going to add is if oxygen is with fluorine. Fluorine gets the negative and oxygen would have a positive, or would be determined after. One of the big things is to remember that the most electronegative element, so electronegative, gets its charge. If we're not talking about ionic compounds, like its oxidation number, whatever charge it would form as an ion, it would use that as an oxidation number. So since fluorine is more electronegative, it'll be negative, and then oxygen, if it is bonded to it, will change. So oxidation numbers for monatomic ions always equal their charge. So group 1 ions are always +1, group 2 are always +2, and fluorine is always -1. Oxidation numbers of neutral compounds sum to 0, and the oxidation numbers of polyatomic ions add to the charge of the ion itself. Okay, there are some exceptions to the group 1 and group 2, but those are what the rules are for AP chemistry. Okay, so if you take additional chemistry and they tell you different, it's because they're diving deeper into the content and telling you and teaching you about exception rules. Okay, so combustion reactions are examples of oxidation reactions. The products of hydrocarbon reactions are always carbon dioxide and water. We see that it is a redox because oxygen goes from 0 to -2 oxidation state, and then carbon goes from -2 to +4. So we do know that redox reaction is occurring because we have changes in the oxidation state, where we see oxygen is reduced and thus gains electrons, while carbon is oxidized and has lost electrons. Precipitation reactions frequently involve mixing ions in aqueous solution to produce insoluble or sparingly soluble ionic compounds. Okay, all Sodium, potassium, ammonium nitrate salts are soluble in water. We talked about SNAP rule, where SNAP indicates sodium, nitrate, ammonium, acetate, which is not mentioned here, but it does apply, and potassium. These are always soluble, so you see them, it's a SNAP solubility. It's a SNAP, guys, so those ones, if it's any sort of anion or cation with these, it is always soluble. Okay, precipitation reactions are a subclass of double ionic replacement reactions. They result in an insoluble product. These are not redox reactions. Okay, oxidation numbers don't change. They just trade ionic partners in the little weird square dance of double ionic replacement reactions. So you should be able to predict the products of a reaction by recombining positive ions and negative ions, switching the partners. You will need to remember that group 1 metals, nitrates, ammonium ions are always soluble. So the SNAP rule, that is something you do need to remember. Beyond that, the AP test will give you additional clues to determine if something is insoluble or not. Okay, they will tell you solid lead iodide is produced. Now or lead 2 iodide. Now you would need to know naming rules and be able to write that equation. But they would give you enough clues so you don't have to memorize what would precipitate. You just need to remember what will always dissolve. Okay, so let's look at some examples. Sodium metal reacts with a solution of sulfuric acid, H2SO4, to form hydrogen gas in a solution of sodium sulfate. So we first need to write our balanced equation. So following the question, sodium metal, we can assume that that is a solid, reacts with a solution of sulfuric acid, so H2SO4, and since it says solution, I can say that that is aqueous. And it forms hydrogen gas, so hydrogen by itself is H2 gas, and a solution of sodium sulfate. And so since it's a solution, we can write aqueous. Now we need to balance it. I can leave the polyatomic sulfate ion together and balance it as is. So I count on each side of the reaction arrow, and I see that I need one more sodium, so I'm going to write a 2 here, so that changes this to 2, and both sides now have the same number of each atom. Now I'm able to assign oxidation numbers. So I'm going to carefully write out all of my species here, so it's a little easier and I have some room to work. Okay, so for anything that's elemental, so it exists as it would in nature without bonding to anything else, so it's by itself, its oxidation number is always 0. So that means sodium is 0, and hydrogen, being a diatomic element, when it is H2, so it is by itself, it is 0. Next, we can assign charges as oxidation numbers. So that means that sodium here would have a +1 oxidation number because that is the charge on it. This 2 comes from the sulfate ion's charge, and it needed the 2 for the subscript to make the overall charge of this compound 0. Okay, we can do the same thing for the sulfuric acid solution. If we know that this is 2-, hydrogen must then have a 1+ oxidation state. And some people ask, what's the difference between a charge and an oxidation number? Does it matter where stuff goes? A charge technically has the plus or minus symbol after the number, whereas the oxidation state has it before. That is not something that is directly tested, but it is just a clarification. That's why the numbers flip around. Next, we can assign either sulfur or oxygen. You give the most electronegative element its charge first. So oxygen being more electronegative, that makes it easy because usually oxygen is the one that you're going to assign next. Oxygen gets a -2 because that is the charge it tends to form. That is the amount of electrons it tends to want to have extra beyond what it normally does. Okay? So that leaves sulfur open for us to determine its new oxidation number. So using some algebra, we can say 2 hydrogen atoms plus sulfur plus 4 oxygen atoms has to equal the overall charge on this compound, which is 0. Solving for S, we see that sulfur must have a +6 oxidation number in order for this compound to have an overall charge of 0 or an overall oxidation state of 0. Okay, so we can repeat the same process for the sodium sulfate. 2 +1s from sodium plus sulfur plus 4 -2s from oxygen has to equal 0 because that's the overall charge of the sodium sulfate compound. When we solve for S, we also see that that is +6. Okay, so we have assigned oxidation states to all of these. Now, if you have to do this for the AP test, you don't have to show all of this work, though it might help you to check, especially for things like sulfur, and make sure that you are solving it correctly. So we're now going to do C, where we use the oxidation numbers to determine which substance was oxidized and which one is reduced. Okay, so we have to look for ones that are changing. So sodium is the first one that we see changing. So sodium goes from 0 to +1. Now, is that a loss or a gain? Well, becoming more positive means you're losing out on negative charges. So this is a loss of electrons, and that means that it is oxidation here. So sodium is being oxidized. Repeating the process, we look for another one that is changing, and we see hydrogen goes from +1 to 0. So that means that it is gaining, and this should always be coupled, right? If something loses, something else must gain. So this is a reduction. So sodium is oxidized and hydrogen is reduced in this reaction. Okay, so now we're going to look at this. We do complete the reaction between nitrous acid, HNO2, and the hydrogen sulfate ion. Then identify the acid base, conjugate acid, and conjugate base. So HNO2 plus HS, and we can assume that these are aqueous because they're saying acid, and this is an ion, it must be aqueous. And then we have to finish something. So I can either give the hydrogen over here, or the HS, the hydrogen sulfide ion, can accept. Turns out that this is easier to move the hydrogen over here, because leading H, that means that this is an acid, and the acid says that it is a proton donor. So it is going to give the proton to the other species in our reaction. So we end up with NO2 minus, because it lost a hydrogen or a proton. So it's now negatively charged, so AQ, plus H2S. Okay? So now that we have moved the hydrogen and completed our reaction, check that it's balanced, and we see that it is, we can now assign our acid, base, and conjugate pairs. So we already told in the question that this must be the acid. And since we are giving the proton to the other species must then be the base, because it is going to accept the proton. That means that it is a base. Partnering these, we see the nitrous or nitrite ion on the other side. That means that the nitrous acid and the nitrite ion are conjugate pairs. That means that this is its conjugate, And since this is the acid here, that means that it must be the base. We repeat the process with the other species pair, and that means that H2S, or dihydrogen sulfide, or hydrosulfuric acid, is the conjugate, and as hinted by the name, that is the conjugate acid, because the base has to have a conjugate acid pair. Okay, and the way to also check this is if you flip the arrow around, and we wrote it this way, does the acid give a proton to the conjugate base? Does the conjugate acid give a proton to the conjugate base to give you the other side of the reaction? If it does, then you wrote it correctly. So we're going to flip the arrow back around, so that way we're all straightforward. Okay, so continue to practice with the You Do questions, checking your answers as you go, and thank you for tuning in.